All right, so it looks like it's 3 p.m., so I'd like to get started. Just a few notes at the beginning, as usual, regarding just sort of etiquette during the talk. If you can please remain on mute when you're not asking a question, and you can raise your hand and if you have a question during the talk, and you can type your question in the chat. And I will notify the speaker that you have a question, and you can unmute yourself and ask it. So I believe that is all. Without further ado, we are happy to have Yuan from Stony Brook University speaking about family Floer program and non-Archimedean SYZ mirror construction. All right, so
thank you.
Go ahead.
Okay, thank you for the invitation. So the title is Family Floer Program and the Non-Archimedean SYZ mirror construction. Okay. So let me begin with a review of SYZ's picture. Suppose we have a Lagrangian ΦIBration, possibly with singularities. And let me take the smooth locus, which I denoted by B0. And let me denote it by the fiber over Q. Let me denote it by LQ, the fiber over Q. And according to Arnold-Liouville's theorem, we know that all smooth Lagrangian fibers are torus. And this smooth locus has an integral affine manifold structure, which roughly says your B0 locally looks like Rn. And if we take this restriction over B0, and this gives you a Lagrangian torus vibration. So now if we follow, that's why this idea of T-duality, then the mirror space could be obtained by taking a dual vibration. So that, okay. I mean, I just, vibration, I mean, for each fiber is a Lagrangian in this symplectic manifold.
Let's see.
Yeah, this is just some background. It's some motivation. So classically, the dual fiber is expected to be this first cohomology group of LQ with coefficient U1. So you can identify this with the space of all flat U1 connections on LQ up to gauge equivalence. And you can see this is also a torus because LQ is a torus. So you can roughly think of this X0 check defining in this way as a dual torus vibration. So this is rough.
Hey, you have a question from Marco Castronovo.
Yeah. So
Marco, you can go ahead and unmute yourself.
Yeah, I think he already answered.
Oh, okay.
Say the map whose fibers are Lagrangian.
Sounds good.
Okay, this is just some background. It's not very precise, but anyway. So the point I want to make is that this T-duality need to be modified by the so-called quantum corrections. So which are given by counting holomorphic disks in this relative homotopy group, pi2xl. So basically we are going to study Lagrangian flow theory for all these Lagrangian torus. But I need to say that we still require this LQ is a smooth Lagrangian fiber. And well, but I found some pictures from the internet. So our holomorphic disk, the boundary of our holomorphic disk is still contained in some smooth fiber. This is the boundary, it's still in some smooth fiber, but its image can go anywhere in your symplectic manifold. So for example, it can intersect with your singular fiber, and which may somehow gives you more information. So this quantum question may include more information outside the torus vibration. For example, you may get in touch with those singular fibers, and you may also intersect with toric divisors, just like the works of Fukaya or Ota Ono on compact toric manifold. In their work, Maslov-two disks play an important role, and this gives us something called Landau-Ginzburg potential. So quantum coercion should be necessary in the story of SYZ picture. So namely, we are going to study Lagrangian flow theory for the family of all these torus fibers in the same time. So this somehow gives you the name family flow. The family flow theory is invented by Kenji Fukaya in around 2000. And later, Tu and Abazoid made great progress along this idea. Roughly speaking, family flow predicts that the dual torus fiber of LQ is not our classical torus, which I mentioned before. It should be something I call the non-Archimedean torus. So you just replace your coefficient U1 by U lambda. So what is U lambda? U lambda is something called, is a multiplicative group of the navical field. So navical field is defined in this way. And I will define U lambda later. So here, you can think of this navical field as an analogy of this field of rational formal power series. The difference is just we only allow integer power for this field, but here we allow real powers, real numbers. And they are both non-Archimedean field, and I will explain this later. Previous family flow works more or less rely on the so-called tautological unobstructed assumption, which says there is no holomorphic disk in Pi2ML. But we think this is too restrictive. So this comes with the first motivation of my work. Can we somehow drop or weaken this assumption? Why? Because these disks are the quantum questions we need. So let me go back a little bit. We want to include this disk. And in particular, Maslov-two disk, as in Fukaya or Ota Ono's work, should give us Landau-Ginzburg potential. Maslov-two disk should give us Landau-Ginzburg potential. And on the other hand, the expected mirror it's in the beginning just a union of all these non-Archimedean torus. This is just a set. And I would like to say it is a very delicate issue to put an analytic space structure on this set. So this comes with the second motivation. So we try to develop a rigid analytic space structure on this set from the ground up. So I mean, I want to be more careful about this rigid analytic space structure. Like I want to say what is a local chart and what is a transition map, and why this transition map is well defined, why this transition map is independent of choices, and why this transition map satisfies co-cycle conditions so that they can glue together. So there are many delicate issues. So for example, you may see that A infinity homotopy appears in Lagrangian flow theory actually correspond to isomorphism of rigid analytic space. There's some homotopy in A side gives you an isomorphism in B side. Okay. Now let me describe the main theorem. Suppose we have a Lagrangian torus vibration on an open subset for closed implementable. So here U is just some subset of M. We don't assume the vibration is on the total on the whole space. For example, the easiest example is comparatoric manifold. And in this case, this pi is given by the moment map. And the main theorem is like this. So we assume Maslov indices of pseudo-holomorphic disk are non-negative. Then we can associate to this pair M pi a triple M check, W check, pi check, consisting of first a lambda rigid analytic space M check. You should think of this as the mirror space of your original M. And you also have a global function W check defined on this M check. You should think of this as a Landau-Ginzburg potential. And finally, you have a projection map on the same base. And you may think of this as a SYZ dual ΦIBration, but it's a kind of a non-Archimedean SYZ dual ΦIBration. So this is my title, non-Archimedean SYZ mirror construction. And moreover, this triple is unique up to isomorphism of a rigid analytic space. So this is a good point because our mirror construction is now independent of choices. And I also remark that Conservator-Soberman once proposed to use non-Archimedean geometry to study mirror symmetry. And we somehow justify this proposal. Okay, so this is the main theorem. And I think we should first review what is a rigid analytic space. Okay. So let me review some basic things of rigid analytic space. And I think this is a good idea to compare it with our usual algebraic analytic geometry over C. Okay, so first, we have navical field. So the navical field admits a valuation map defined by sending such an element to the smallest power, E0. And this valuation map is equivalent to a norm defined in this way. And this norm gives you an adic topology on the navical field. And a field which admits such a valuation satisfies some properties is called a non-Archimedean field. And remember our multiplicative group we mentioned in the beginning. So U lambda is just the subset of all elements with zero valuation. And equivalently, it is a subset of all elements with norm 1. So it is very natural to think of this U lambda as an analogy of U1, our circle. So let me go back a little bit. So we go from U1 to U lambda. So this is somehow justifies this name, non-Archimedean torus. U lambda to n. Okay. And we are also interested in navical ring. And this navical ring has a unique maximal idea defined in this way. And this lambda plus is used to hold quantum correction data. For example, if you have some holomorphic disk, which is a non-constant, then the energy is positive. So this disk should be included in this lambda plus. And you can see U lambda is, and the lambda 0 has such decomposition. Okay, let me begin this comparison. So over C, we often consider the polynomial algebra. This is the most basic algebra over C. And if we work with navical field, what we consider is something called Tate's algebra, denoted by Tn, which is defined by the set of all formal power series, so that its coefficient satisfy this. But there is a better way to understand this Tate's algebra. it is just all formal power series, so that which converges on the unit ball. Okay, so the polynomial algebra corresponds to affine space, Cn, and Tate's algebra corresponds to the unit ball. So here, spec is like the spectrum of prime ideas, and SP is spectrum of maximal ideas. So basically, each point in the unit ball gives you a maximal idea of this Tate's algebra. And you can see every element in this Tate algebra gives you a global function defined on the unit ball. Okay, and over C, we often consider some variety, some affine scheme given by the spec of Rn modulo some ideal A. And similarly, over navical field, we consider the affinoid space, which is defined by a similar way. But we just will replace Rn by Tn. And this is called a affinoid space. And this Tn modulo A is called a affinoid algebra. And if you glue many affine schemes, you get a variety or a scheme. And if you glue many affinoid space, you get something called rigid analytic space. This is the definition of a rigid analytic space. So rigid analytic space here for our mirror space. And over C, it is popular to consider this formula, this function defined by sending Zi to the logarithm of norm of Zi. And this is a torus ΦIBration. But over the navical field, we consider this map, I call it CHOP. You map Zi to the valuation of Zi instead. So you should think of this as a non-Archimedean torus ΦIBration. For example, its fiber at 0 is our non-Archimedean torus, because the fiber at 0 is like the valuation of all Zi is 0, and the valuation of Zi is 0, then this gives you U lambda. And here you have n copy of lambda plus, so you have n copy of U lambda here. Okay, so this is the so-called non-Archimedean torus ΦIBration. Now let me describe what should be a local chart of our mirror space. So our claim is that the dual ΦIBration map pi check is locally given by this non-Archimedean torus ΦIBration. And we should consider the so-called polytope domain, which is a pre-image of some rational polyhedron in Rn. So here rational polyhedron means your normal vectors are rational. Normal vector of faces are rational. So why this is good? Because it is a affinoid space. So let me recall, a affinoid space is something similar to a affine scheme. So it's like a building blocks. And this affinoid space corresponds to some affinoid algebra, which we call polyhedral affinoid algebra. And well, by definition, this is defined in this way. But anyway, you can forget about this complicated definition, and you can look at this. So this polyhedral affinoid algebra just consists of all formal power series, which converges on this polytope domain. And you can definitely see some similar patterns, right? Because remember here, Tate's algebra is defined in this way. And this converges just, we just replace our unit ball by this polytope domain. Now in our situation, the base B0 locally looks like Rn. So remember our by Arnold-Liouville's theorem, we know B0 is an integral affine manifold. And the claim is that we can still define this polyhedral affinoid algebra, where Q is some point in B0, and this delta is some rational polyhedron in B0. This is because the GLNZ transformation preserves the rational condition. So if you have a rational polyhedron in one local chart, then if you take some transition map, it gives you another rational polyhedron. So it is well defined. I mean, you can still define a rational polyhedron in this affinoid, in this integral affine manifold B0. So basically, you think of this delta as some subset of Rn, and the Q is like Q somehow indicate where is the origin. So this is the meaning of this notation. Is somehow similar to this. Now, example, if delta is just this point, then you get this non-Archimedean torus, which is a pre-image of the zero. Okay, so now let me claim that our mirror space M check is locally given by a closed analytic subvariety in the polytopic domain, cut out by the ideal A of weak Maurer-Cartan equations. And let me explain weak Maurer-Cartan equation. And this idea will be defined later. So following Fukaya or Ota Ono, we can associate to L a filtered infinite algebra defined on the dynamic homology group. And you can decompose each MK like this, where beta is some class in pi to ML, and the E of beta is the energy. MK beta is such a map of degree 2 minus k minus mu beta, which is given by counting holomorphic disks in class beta. So you have a collection of operators, and they satisfy infinite equations. And Gromov companies can imply this M converges for adic topology. So remember here, M is this MK is actually has infinite terms. So you should prove this is convergent for the adic topology. And you also need to use some homological perturbation to obtain this M, which in the literature is called the canonical model. But I don't want to discuss this today. Okay, so anyway, you have some infinite algebra for all this Lagrangian, for any Lagrangian fiber. Now let me define the Maurer-Cartan equation. Just defined in this way. And there is an important property of this M, which says for any B in the first cohomology group, we have the following divisor axioms. So if you have K input and you insert B into some between XL minus 1 and XL, and you take this sum, and you get this identity. And if you apply some combinatoric argument, you can see MK beta BBBB is equal to this. And here this MK beta B BBBB is appeared in this Maurer-Cartan equation. So by divisor axiom, Maurer-Cartan equation can be transferred to the following simpler one. So remember here we have sum over both beta and k, and now we only have sum over beta, because if you take sum over k for this term, you get the exponent here. And this idea was exactly used in Fukaya or Ota Ono's work on compact toric manifold. Okay, so the idea is as follows. We forget about the original Maurer-Cartan equation and focus on something I call Maurer-Cartan formal power series. So basically, we replace this exponent by this y to partial beta. Here, y is some formal symbol. And we claim this does not lose any information. And actually, we can contain more information. If you fix a basis of H1, then this y to partial beta can be identified with y1 partial 1 beta dot yn partial 1 beta, where partial I beta is this cap product, and this is some integer. And you should consider this P as a collection of series, because M0 beta lives in this theorem homology group, which is a finite dimensional vector space. Now, if we set B equal to the sum xi theta I, then e to partial beta cap B is equal to e to x1 partial 1 beta times e to xn partial beta. So this gives you a point in the non-Archimedean torus given by yi equals to e to xi. And moreover, any point in this non-Archimedean torus can be written in this form. So here goes with our first point. The restriction function on this non-Archimedean torus u lambda to the n recovers your original Maurer-Cartan equation. Here is some computation. So you plug in this y into your formal power series, you get this. And according to the computation at here, this computation tells you you get this. And now you just need to apply the divisor axiom, and you go back to your Maurer-Cartan equation. Okay, so here is your Maurer-Cartan equation. You apply divisor axiom, you get this. But definitely you can reverse this computation. You first have this, and you can go back to your Maurer-Cartan equation. So this restriction function recovers your Maurer-Cartan equation. And we define the domain of convergence of this formal power series. And it is necessary that domain of P contains our non-Archimedean torus. But moreover, the domain of P can be larger. So this is our point 2. P converges on a bigger domain, a pre-image of some delta. Remember, our non-Archimedean torus u lambda to the n is a pre-image of 0. So this point 2 can be proved by the reverse isoperimetric inequality, which is due to Gromman-Solomon. So if you take some small rational polyhedron so that its diameter is small enough, then you can show this P converges on this domain. This implies point 2. And we will later see that P actually contains information of nearby Lagrangian fibers over this small delta, which is a consequence of Fukaya's trick I will explain later. Moreover, there is an important rigidity for this formal power series. This goes with our point 3. So conversely, the restriction function on u lambda to the n actually determines your original formal power series P. So this is because of the following lemma x. So suppose you have some arbitrary formal power series. And I assume this F vanishes on this non-Archimedean torus. Then F is identically 0. So what does this mean? This means if you have something vanishes at the central fiber, then it vanishes everywhere. Okay, let me go back a little bit. So first you have a restriction function. You recover some Maurer-Cartan equation, and your domain can be enlarged. And this restriction also determines your original power series. And this lemma x exactly implies 0.3. The proof of this lemma x is not very difficult. You just need to use some non-Archimedean analysis. But this lemma x turns out to be very important. For example, later we will show some wall-crossing formula. And this will imply transition map are well defined. So here we are discussing local chart. And after we have local chart, we need a transition map to glue them. Okay. Now, this is the last page of our local chart. So notice that by degree reason, M0 beta lives in H2 minus mu beta. And we also assume Maslov index is non-negative. So it is very natural to consider the following decomposition, because basically you only have two possibilities. Mu beta is equal to 0 or 2. Okay. And we decompose our Maurer-Cartan equation like this. So here W is given by the first series here. And the QPQ are just the second series. But here CWQ is some basis of H2. And let me recall that delta is small. If delta is small, then the domain of P contains this polytope domain. And this actually implies that this W and QPQ lives in our polyhedral phenoid algebra. Let me recall that. Here, polyhedral phenoid algebra is just defined by this way. As long as you converge on this polytope domain, then it lives in this polyhedral phenoid algebra. Okay, so we have something in this phenoid algebra. Okay, this is the definition. We define our idea A to be the idea generated by all this QPQ. We don't include W, we only include QPQ. So you can think of this as the idea of weak Maurer-Cartan equations. Now, a local chart of our mirror space is defined to be the closed subvariety cut out by this idea. So it's like some zero locus of weak Maurer-Cartan equations. Moreover, this W can be viewed as a function on this chart. And it will be a local piece of our global Landau-Ginzburg potential. Okay, so far we have defined what is a local chart and what is a local piece of global Landau-Ginzburg potential. The next step is to glue them. We have a lot of local chart. We want to glue them. So here is a configuration. We have two adjacent Lagrangian fibers, L and L tilde, over Q and Q tilde. And we have two small rational polyhedron here, delta and delta tilde. And let V of A and V of A tilde be the local chart, just defined as before, just defined in this way. In this way, this is our. And we want to cook up some transition map. But this V of A is some is really some affine space as P of something. So which means it's a analog. This V of A is some analogy of a affine scheme. So you can apply Gross-Seibert philosophy. So which means such a transition map is the same thing as an affinoid algebra homomorphism for this quotient algebras, like a scheme theory. Okay, so our plan is as follows. We first find some algebra homomorphism, and we try to pass to the quotient. And there are two main aspects for the construction here. First, the Fukaya's trick. Second is A infinity homotopy equivalence. So A infinity homotopy equivalence is an A infinity homomorphism, which has a homotopy inverse. Okay, so now let me begin with the Fukaya's trick. So if you choose some diffeomorphism, so that f of L is L tilde, then we have natural identification on the moduli space. So on the left-hand side, this beta is some pi to ml, and the beta tilde is the push forward of this beta. And f star j is the push forward of j. So if U is some j holomorphic disk for the left-hand side modular space, then you can check immediately that this composition F circle U is F star j holomorphic disk. So Fukaya's tricks just says, well, the two infinite algebras, MJL and MF star JL tilde, which are constructed by the left-hand side modular space and the right-hand side modular space respectively. And these two infinite algebras are very close to each other. Basically, this is because counting numbers is the same, because you have identification of a modular space. And explicitly, the relation between these two infinite algebras are described by this equation. And the energy will be changed. And the formula is like this. And please keep in mind this formula. I will go back to this later. Intuitively, you may think of this MF star JL tilde as some push forward infinite algebra of your original infinite algebra MJL. Now, if you choose some local chart around Q, so you can identify Q with 0 and Q tilde with C. And let me record the Maurer-Cartan formal power series. Now, recall that we have discussed before. If we restrict P to U number to the N, we can recover the Maurer-Cartan equation of MJL. We have discussed this before. Moreover, if we restrict this series to the fiber over C, so here U number to the N is a fiber over 0. If we restrict this P to the fiber over C, you recover the Maurer-Cartan equation for this push forward infinite algebra. So this infinite algebra is a push forward of your original infinite algebra. And this is a consequence of Fukaya's trick. Yeah, basically, you need to use these formulas here. But there is some computation to do that. Anyway, using Fukaya's trick, we justify our previous message. P really contains information of nearby Lagrangian fibers, like fibers over this delta, this small delta. Okay, so why is Fukaya's trick useful? So remember, our goal is to relate these two local chart, V of A and V of A tilde. So V of A comes from the infinite algebra of MJL, and the V of A tilde comes from the this infinite algebra MJL tilde. So first we want to compare these two infinite algebra, but this is like you have different Lagrangian fibers. And now if you apply Fukaya trick, you only need to compare this push forward infinite algebra with this MJL tilde. So the good thing is the reference Lagrangian is the same. But you have different almost complex structure. But if you have two different almost complex structure, you can always find a path to connect them. And following Fukaya or Ota Ono, you can find some A infinity homotopy equivalence between these two infinite algebras. So here CF denotes some collection of operator, and you may have some A infinity equations. So this is some A infinity homomorphism. And this MF star JL tilde is a push forward of your MJL. So here approximation notation is to indicate the Fukaya trick. And moreover, the left-hand side A infinite algebra gives you one local chart, V of A tilde. This MJL gives you another local chart, V of A. So your transition map should really use this data, this A infinite homotopy equivalence. So this is the first step of transition map. So we define such a complicated map like this. So let me give, I cannot explain why we need to define this way. So let me give you some intuition. So first, this coefficient correspond to the Fukaya trick. So remember the energy formula. Oops. The energy formula. This is basically this part. This part, right? If you, yeah. So this corresponds to Fukaya trick. And this exponent part corresponds to work coursing. And this comes from A infinity homotopy equivalence. So you look at here, we have this CF0 beta. CF0 beta here. So the main issue, let me say, the main issue is that we expect the mirror construction should not depend on choices. But this map, this algebra homomorphism really depend on choices, like F and the path of almost complex structure. So which is not good. And fortunately, this does not matter for the following two claims. First, we emphasize that what we need is not this algebra homomorphism. What we need is a quotient homomorphism. So this is our claim A. This algebra homomorphism phi f can pass to the quotient. This is our quotient. Moreover, we can show this quotient map. This quotient can map this W to W tilde. So which means a global Landau-Ginzburg potential is very possible. And this quotient homomorphism defines our transition map by star. Yeah, let me go back a little bit. Yeah, this quotient homomorphism gives you a transition map. Moreover, we can also prove that this quotient only depends on the homotopy class of this A infinite homomorphism. So this somehow well, you can imagine this can imply the transition map does not depend on choices. Okay, so we begin with the explanation of claim A. And it will be a result of our workhorse formula. So what is the workhorse formula? So we have such two infinite algebra, M and M tilde. We decompose their Maurer-Cartan formal power series as before. Here 1 and 1 tilde are generated of H0. Theta and theta tilde are bases of H2. And A tilde are ideas of weak Maurer-Cartan equations. So here's our workhorse formula, which is the key to our claim A. Okay, Hiroli Tanaka asked a question. So maybe we can discuss in the end, okay? Okay, so this is a workhorse formula. And let me explain this formula. So here eta is some homologic class. And this pairing is just a natural pairing. And RPQF eta is some formal power series, which like this. But we don't really care about the explicit formula for this R, because we know this sum is just some, well, just some linear combination of Q tilde. And this linear combination lives in our idea A tilde. Okay. So now suppose our workhorse formula is true. Then we first choose eta dual to theta PQ. Then you get this eta comma P is equal to QPQ. And this is 0. So which means here is QPQ, here is 0, and this is something in A tilde. And then QPQ is one generator of your A, another idea of weak Maurer-Cartan equation. So this implies this algebra homomorphism maps your one idea of weak Maurer-Cartan equation to another weak Maurer-Cartan equation. So which means this quotient homomorphism really exists. Okay. Moreover, if you choose eta dual to 1, then this eta comma P is W. So here is W. And this is 1. This is W tilde. So you get YF of W is W, it lives in W tilde plus A tilde. So passing to quotient, which means the quotient homomorphism maps W to W tilde. So anyway, we have proved that as long as the workhorse formula is true, then we have claim A, which means we have quotient homomorphism, and we have, we maps one W to another W. Okay, so now it remains to prove this workhorse formula. It remains to prove this workhorse formula. Okay, so what should be a strategy of proof? This is our lemma X we mentioned before. So let me recall that if F vanishes on the central fiber, then F is identically 0. So which means if you want to prove some identity of formal power series, then it suffices to prove this identity holds when you restrict to this central fiber. Moreover, the navical field enjoys the property that every element in U lambda can be represented by some exponent. So it is enough to prove F1 of it's enough to prove this guy. And if you put B equal to the sum xi theta, then you will see this E2 partial beta cap B. It's like before. You have this, and you can apply divised axiom again, but the backward, like you have some C F0 beta, which appears in your phi F, and you have some Y partial beta, and apply divised axiom, you get this. So A infinity structures in Lagrangian flow theory join the game. So you have many A infinity relation to use. Actually, we already used this idea before. For example, we have this Maurer-Cartan formal power series. By lemma x, it is the same thing as this restriction function. And applying divised axiom, we go back to Maurer-Cartan equation. So basically, we apply the same idea here. Okay, so now we have, let me record the formula for this phi f. And alpha tilde something in the fundamental group. You can think of it as something in Zn. Okay. So let me just go directly to the work-causing formula. Okay, so Kato asked me, why can you represent every element of U lambda as an exponential? So this is because, this is because, so basically you can find some inverse map by logarithm. Like you have some exponential and you have some logarithm, and the composition is identity. So is that okay? Yeah, you should modify some. What? Well, maybe I can discuss this later. I'm sorry. Okay, so let me pick a point in this U lambda to the n. And let me write B equal to, yeah, it will be some infinite power series. And so you can define a logarithm function. For example, I don't know. I cannot explain now. Maybe I can discuss it in the end of talk. It's okay. Okay, so let y be some point in this U lambda to the n. And the b is some sum xi theta. So xi comes from this exponent. And it is enough to compute this restriction. So here is left-hand side of your work-causing formula. And we have discussed that we only need to assume, but we only need to restrict it to U lambda to the n. So we just need to compute this. And recall this P is our Maurer-Cartan formal power series. And it's like this. And you can apply this formula here. So let me draw some boxes. So this is kind of complicated. And these blue boxes, this is because of Fukaya's trick, the energy formula. And because we take the substitution at this y, then this yellow box becomes this exponent. And this green box, you can apply the divised axiom as I mentioned here, divised axiom. So you get something like this. Now here you apply divised axiom of this CF, but we can also apply divised axiom of this M. So you will pour this green box into this M, just as before. You can think of this as some B prime, and this B prime you can also pour into this M0 beta. So you will encounter something like this, MCF dot CF. So you have many copies of this CF, and this kind of thing will appear. So I think many people should be familiar with this. This is just the 1/2 of A infinity equation. So I don't want to finish the computation, but here is a short message I can say. So the work quotient formula is basically equivalent to the A infinity equation of this CF. Work quotient formula is just the A infinity equation of this CF. Well, this is I think this is not completely rigorous because it really involves some divised axiom or Fukaya's trick. But it's morally correct to say work quotient formula is just the A infinity equation. Okay, and this can prove the work quotient formula. Okay, so now we have claim A. This we have this quotient homomorphism, and we need to show this quotient homomorphism does not depend on the choices. So here we should be more careful about homotopy class. I'm sorry, I have to speed up. Okay, so this homotopy class should be, so more precisely, we need to develop an improved homotopy theory of infinite algebra, which I call UD homotopy. So here U is a unitality, D is a divised axioms. And there are some heavy homological algebra, but the idea is kind of similar. You just require 2 additional conditions, unitality and divised axiom. And to prove claim B, we further consider the 2 aspects as follows. So for B1, which says for different choices, you may have something UD homotopic to each other. This is basically okay. And we need, okay, so let's focus on this B2. So by their defining formula, we can write in this way. So we have some phi f and we have some phi f prime. And there are some error term like this. So it suffices to show the error term lives in your idea of McMurrich-Cartan equation. And if so, you can, if you quotient out this idea, then you get the same quotient homomorphism. Co-cycle condition will be proved using similar ideas. Like you may have some phi ik and phi ij, phi jk, and you compare them and you consider error term, and you show the error term lives in the idea of McMurrich-Cartan equation. Okay, so anyway, this is proved by some homotopy theory, and I don't have enough time to discuss this. So let me just summary my talk. So if you have some infinite algebra, you can get Maurer-Cartan equation. And this Maurer-Cartan equation gives you local chart. And if you have some infinite homomorphism, this gives you work-causing formula. And this work-causing formula gives you transition map. And this transition map is some quotient. And this is well defined. And furthermore, if you have some homotopy of infinite homomorphism, then this gives you, I mean, this can imply the error term lives in the idea of weak Maurer-Cartan equation. And this implies transition map. Transition map is independent of choice. And you can also apply this idea to show the co-cycle condition. Okay, thank you.
Great. Thank you so much, Hang. So clap, clap, clap. Hiro, did you have a question you wanted to ask?
Yeah, someone has a question.
Yeah, I've got a couple of questions, but I don't want to hog it. I'll just write it in the chat.
Okay.
And if there's time to answer it, please do. But otherwise, I can just send you an email too.
So let's do Hiro and then Barish and then Marco.
Yeah, I mean, mine was a minor algebraic question. It's just I was a
Okay.
little confused about the non-Archimedean versus Euclidean topology. I think we can still define this, t-adic logarithm on u lambda or part of u lambda, but I feel like, for instance, you can't represent 2 as an exponential.
Okay, so
because log of 2, you can write x log 2, but that's not convergent in non-Archimedean topology.
no,
Let's do Hiro first, then we'll do that one.
can I draw something? I don't know. Okay. Oh, so you mean u lambda? So you have some lambda 0. So you have some exponential map. But actually you can like module 2 pi I.
I think the exponential defined on lambda plus.
Maybe I can share the iPad screen. Maybe this is better to explain my idea. Is it okay? I can share another screen.
Don't worry too much about it. It's just, mine is a minor algebraic question. Prioritize other questions.
That's fine. Then let me show you. Okay, can you see the board?
Yeah.
Okay, so here's the thing. U lambda is C star direct sum lambda plus. Lambda 0 is C direct sum lambda plus. So you define your exponential U lambda. So here you have some x. You write x0, x plus. X0 is in C. Oh. X0 is in C, x plus is in lambda plus. And you define this exponential to be e to x0. And you have some form power series, the Taylor series. This is the definition. And you can also define the logarithm. So if you have some y, and you write this y as y0 plus times 1 plus y plus. Say the logarithm of y, like logarithm of y0 plus, so here y0 is in C plus the logarithm. The formal series of logarithm like this. Yeah, this is your definition.
Okay, thanks.
Okay, it's
That
okay.
answers my question.
Maybe this is more clear.
Yeah, it's clear. Thanks.
Okay, no problem. Oops.
Hiro, did you want to ask your question?
Have answered your question?
Sure. You prefer that I do it over audio?
Let me share the screen. Okay.
Yeah, so I had I have two questions. The first of which is very naive. So normally when I think of transition maps, I would not think of a map from one chart to another, but I would also, I would try to construct a map from the fiber product of the two. And also the way that you drew the pictures somehow,
Yeah. Okay. So actually, you need to consider intersection. Here,
Okay.
I'm kind of. So here delta is really some intersection. Delta cap delta tilde.
Okay, great.
Yeah.
And then
But I don't want to say too much notation in this slide. So
okay, great. Can I ask a follow-up question?
yes.
So if I understand correctly, you've created some non-Archimedean mirror living over B naught, the non-singular locus of
Yes.
the SYZ ΦIBration. So I don't know much about non-Archimedean geometry, but is there a notion of something like a Nagata compactification?
I have no idea about compactification. maybe you can tell me about this. I don't know. I just yeah. I don't know compactification. So I think so my construction is like this. We need a sequence of a compact domain of this B0. It's like you have some composite, and you construct some mirror at this over this composite, and you have a sequence of composite which exhausts this B0. Something like this. But I don't know how to compactify to B, because I think if you have some singular fiber, this kind of argument does not apply, because you don't have torus, and you don't have some formal power series in here.
But my question actually wasn't about constructing the correct mirror. My question was about whether or not you could get more information by using a cheap trick. Which is, informally speaking, you could think of your mirror living over B naught, as something that's maybe quasi-projective, but definitely not compact because it's missing the fibers over the singular locus.
Yes.
But in algebraic geometry land, like any reasonable variety has a Nagata compactification, which is not exactly universal, but it's close to some universal proper thing that you can embed into. And because you also have this, superpotential, I was wondering if you could, formally deduce anything about what the superpotential might need to look like if you do extend to some proper thing that contains your mirror.
I don't know. Yeah, this is a good question to ask about compactification, and maybe we can discuss later.
Okay, thank you.
Yeah, thank you for the question.
Okay, I believe Marco was next.
Yes, so thank you. I wanted to ask if you can say again where precisely in your construction the polyhedron delta comes from. Or the polyhedra, I guess you had many, so.
This one, rational
Yeah.
polyhedron. Oh, this rational polyhedron is just it's just something like this. But the normal vector is in Zn. This is your delta.
So but here I read delta in Rn is a rational polyhedron. So you just take any rational polyhedron. How do you pick this polyhedron?
So I mean, you have some hyperplane. So this plane is something like Bij, Xj. I don't. And this gives you a half plane, Ci. Yeah, something like this. So this Bij gives you some vector in Zn. And you have a copy of this, you have a system of this inequality. And this gives you this rational polyhedron.
Okay.
Yeah, I'm not global. Yeah, this rational polyhedron is small. It's not very, I mean, on Rn you can be very large, but here you must require this is very small.
So but I guess what I'm confused about is that okay, you seem to pick this polyhedron around the base, like around the point in the base where your Lagrangian fiber leaves over, and
Right.
but then the way you choose the polyhedron doesn't seem to use in any way the information of the फ़ibration, the Lagrangian फ़ibration.
But the फ़ibration guarantees you have integral affine manifold structure on this base P0. Otherwise, you cannot say, because you need to, I mean, these transition map are all in this GL and Z, so which preserves the rational condition. So this is a consequence of the Lagrangian फ़ibration. Yeah, maybe.
Okay, thank you.
Okay, I think we had one more question from Yang Li.
Hi, so I was wondering, so it looks like from your talk, you don't actually need any assumption on singular fibers, is that correct?
Yes, I didn't. I mean, I only, yeah, just like here, we only consider smooth locus, B0.
Right, but suppose, for example, that my discriminant locus is actually codimension 1 in principle, and suppose this thing cuts the base into several disjoint pieces. I mean, does it cause any problems for you? Or, I mean, in that sense, I mean, is it still a reasonable mirror? Or does it just not happen in practice? Or, I mean, is it somehow a priori ruled out by this special Lagrangian फ़ibration condition or something?
So maybe I say some connected component, I think. Maybe this is better. So yeah,
But
here,
is there anything coming from your assumption which says that the discriminant locus can't be too bad?
no, I just assume a Lagrangian torus फ़ibration over B0. B0 is some, I don't know, B0 is some base manifold. Maybe you can assume this B0 is connected.
Okay. And your result also works in general dimensions, not necessarily 3. Is that correct?
Yes. But you need to require this assumption, non-negative.
Okay.
Maslov-Weights are non-negative.
Is it a kind of generic assumption?
Yeah, I think this is kind of a essential assumption.
I'm asking you, is it completely generic? So,
But I think, for example, if you have some special Lagrangian, this kind of assumption should always hold. In
okay.
most cases.
Yes. Okay, thanks.
No problem.
All right, so it's 4:15, which is the official end of the Q&A. If you'd like to stay and discuss more with the speaker, you are welcome to, but let's give another round of applause to Hang.
Thank you. Yeah, here only Tanaka asked a question about matrix factorization. Well, I think this is a good question. So I have no idea what should be a matrix factorization on rigid analytic space. Yeah, I'm still working on this. So at least locally, if you have some Lagrangian section and you have an infinite bimodule, then you will get matrix factorization, at least locally. Aris Kata asked me.
What I wrote was just to Hiro.
What's your question?
No, I mean, I was asking to Hiro whether you don't need algebraicity or something of that sort for co-modular perf type results. It's the continuation of question of Hiro, essentially. It's not a separate.
So can you ever plug in a value for this T to get like a single mirror? I mean, like, do you get like a family of mirrors, or is you just only think of it as an analytic space?
I think just one single mirror space.
Okay.